Now we will consider a conceptual example about the motional electromotive force. It's a bit different than the setup that we have considered, but the principle is the same, and effectively it is the same. So the setup is that we have a region where we have a uniform magnetic field, and we have here a rectangular loop of length L and width W. Its width is W, and then this is pushed with constant speed into this region. So it enters this region. This region has a width of 3W, and then it exits that region, moving all the way with this constant velocity v to the right. Now, we are first required to plot the magnetic flux through this area as a function of x. X is this horizontal coordinate. Now, of course, here, when it is just here, there is no magnetic flux. As it enters, the magnetic flux starts to increase because the flux only will be through an area equal to L times x, because when it enters here, the x coordinate of this end represents at the same time how much of it is into the magnetic field region. So the flux will be, in this case, L times B times x. And so it will be a function that will increase linearly with x from 0 until it reaches the max. When it is totally into the region, when x is equal to w, then BLW is the maximum flux that it has. Now, as it moves here, the flux is constant at this value because the magnetic field is uniform. Now, when it starts to exit, it will go down with the same slope because it's moving with the same speed. To move with the same slope and come down to 0 totally when it totally exits the region where we have a magnetic field. So this is the phi, the flux as a function of time. Okay, so the flux is varying between x equals 0 and x equals w. It's constant between x. It's constant between W and 3W, then after that it's decreasing. Okay? Now this is important because in the next step we are requested to plot the induced motional electromotive force as a function of x. Now, since the flux is varying only here, and here I don't have any variation in the flux, and here only, then there is an induced electromotive force only between 0 and omega. There is 0 induced electromotive force here because the flux is not varying, and there is also an induced electromotive force here. Now, because the flux here is increasing, and due to the minus sign in Faraday's law, if we want to keep that minus sign, then E will be minus d phi by dt. So phi is increasing here, so I expect, so d phi by dt is positive. I expect the flux to be, the electromotive force to be negative in this region and positive in this region. And this is what we are having in this case. So as you can see, we have a negative flux here, a negative electromotive force here, and a positive electromotive force here. Why is this? As I mentioned, here, if you look at this quantity, now the flux here is varying. If you want to find what is d phi by dt. Now, what is phi? As I have said, phi is BLX. Is BLX because as this enters here, then the part of the rectangular loop here, part of this area that is having flux is actually, it is of length x, where x is the coordinate of this front here. Okay, so the flux is BLX. B and L are constants. So when you take dB by dt, d phi by dt, I'm sorry, you will get BL dx by dt, and dx by dt is V. So the flux will be V in this case. All the way will be the way until this enters here totally. Okay, and this is why, but we have a minus sign, so it will be minus BLV. The same applies here. When it's exiting, here it will be minus BLV, and therefore with a minus sign it becomes BLV. So this is the magnetic flux in as this is entering, this is the electromotive force that is generating. In this region, when it is totally inside the magnetic field and the flux is not varying, then there is no electromotive force generated. Now, in part C here, we are requested to find the external applied force necessary to counter the magnetic force and keep V constant as a function of X. Okay, so we want here what happens is that, as I said, when this enters here, then when we have an induced current, then in this case the magnetic field will exert a force, and this force, as we have shown, is opposing the velocity. Okay, and so you need to have an applied force equal and opposite to this magnetic force in order to keep this moving with this constant velocity. So we want to find what is this magnetic force. Of course, this magnetic force will occur when you have a current only, because when you don't have a current, then there is no magnetic force acting in the loop. So when the loop is totally inside here, you don't have a magnetic force. So the magnetic, therefore you don't need to have an applied force to keep it moving with velocity v, because if it already has that velocity, it will not be resisted by a magnetic force, because that magnetic force doesn't exist, because when it is here there is no electromotive force and there is no current, and therefore there is no magnetic. So here between omega and 3 omega here, the magnetic force or the applied force is 0 because the magnetic force is 0. Now while it's entering here, what is this magnetic force? The applied force should be equal and opposite to the magnetic force. What is the magnetic force? Well, ILB. But what is I? I is E over R. E is the induced electromotive force, and we have seen that the electromotive force, the induced electromotive force, has an absolute value, ILV. So it's ILV over R. This is I multiplied by LB. If you do carry out the multiplication, then this is the applied force that is needed to counter the magnetic force in order to keep this moving to the right with constant velocity. This applies here, and it also applies when this is going out. Of course, this force is acting, when this is entering, is acting only on this part, on this length only. Why? Because this part is still outside. Okay, and it also this part is outside, and also it is even when these are N, and these two sides, the up and down side, they have current, the force on these, magnetic force on these, will be in opposite direction, so there will be not zero net force here on the upper and lower one. This one will not feel a magnetic force because it is not within the magnetic field. The same applies here. When this starts to go out, then only the part that is still inside the magnetic field is the one which will feel this force, and it will be to the left, and the magnitude of this force is this. Okay, so that's the answer to this question. Now this example is a bit more involved, but it's a very interesting situation actually. So what it says is, first you make this rod in this circuit move with constant velocity. So you have an applied force, and then you have opposing magnetic force. So you keep it, you speed it up until it reaches a constant V, and you leave it moving with this constant V. Okay, by pushing by F applied, which is equal to FB. Then after that, you decide to remove this F applied. Okay, after it had reaches V, you remove this F applied. But still, this has still a velocity moving to the right. Okay, and now because there is a current now in the induced in the circuit, then there is still an FB. So what will happen is that this will start to slow down. This will start to slow down. Okay, this is the situation that's happening. So the question is, using Newton's law, find the speed of the bar as a function of time as it's released. Yani, when it has this velocity v and only Fb is acting, okay, and you remove F applied, it will start slowing down. So meaning that its velocity will be changing with time. So find how does this happen? What is the explicit time dependence of its velocity after it reaches a velocity v initial, call it v initial, and you remove the applied force. So as it slows down, okay? Now, well, we say in this case that it will be subject, according to Newton's law, there is only a single force acting, which is the magnetic force in the opposite direction in this case, and this is equal to the acceleration. The magnetic force in this case, if I take the positive direction to the right, then this magnetic force will be minus ILB, this minus sign, because it's pointing to the left, and it is equal MA. But what is A? A is dV by dt, okay? Now, here we have an interesting situation. Okay, this is A is the dV by dt, but I here itself also depends on the velocity. So the velocity is changing, so I is changing. So I have m dV by dt, but also I here is a function of velocity. Why? Because what is I? It is E over R. And what is R? What is E, the electromotive force? It's ILV, okay? BLV. So exactly, this is what we have here. So we write it here by substituting for I, BLV over R multiplied by LV. So you now get a differential equation for V in this case. So it says m dV by dt is equal minus BL square over RV. This is what we call a first order differential equation, okay? And the solution is standard and similar. This is similar to what you have got, the equation that we got actually in the case of the capacitor. It's a simple first equation. So you just arrange terms, so you put the V's on one side and you bring this to the other side. Now dV by, over V is equal to this, multiplied by dt. All of these now are just constant, okay? None of them is time independent. Mass, R, B, L, they are constants, and so you can integrate this immediately. You integrate this from V initial to a given V, and you integrate this from 0 to any time t. Once you carry out the integral of this is len, the integral of this is just linear, dt is t, and you get this, and if you take the len of both sides, then this is the expression you get for the velocity as a function of time. Tau here is just this constant. You define this quantity, you call it tau, and you get V equals V initial e to minus t over tau. Tau is a constant here, which has to do with the mass, with the resistance and the magnetic field and the length and so on. So as you can see, this is a decaying function. At t equals 0, V is equal Vi. As time passes, V drops exponentially. We expect it to drop, but here this is the precise form of its time dependence. Okay, quite an interesting situation. Now show that the same result is found by using an energy approach. Let's apply energy consideration and so that you can get actually the same expression for the time dependence. Now here the energy consideration is that the rate of change of the kinetic energy of this is equal to the rate of change of dissipation of power here. Now, so dk by dt is equal P electric, and this is equal minus I square over R. This minus sign, why? Because because the energy, K, the kinetic energy is decreasing in this case, so you need to have a minus sign here. So when you do this, what is the kinetic energy of this bar? It is 1/2 mv squared. So how does this change with time? This should be equal to the power that is generated, the power that is dissipated in the resistor, okay? Up to a minus sign, of course, to keep, because this quantity is decreasing, okay? If you would keep this plus, you will see that it will be, V will be growing with time, which is impossible. So that's the physics of it, that the rate of change of the kinetic energy here is equal, which is the power in this case, the rate of change of energy is power, okay, and is equal to this. So once you take the derivative of both sides, you get this, this side, you get, and arrange things, you get this expression. But what is this expression? It is nothing but this expression that you have got here. It's exactly this. So proceeding in the same way, take m to the other side, and you will get the same equation. You see? So take m to the other side. It's exactly the expression that we got before. And so after that, if you integrate, you will get the same expression for the velocity. Okay? So you can get it from here too. This last example is about motional electromotive force. That is, we have a conductor moving in a magnetic field, and it is not a part of a circuit or so. Okay, so we want to find what is the potential that is generated across this conductor. And our conductor in this case is not a conductor performing linear motion, but it's a conductor that is performing rotational motion. So think of a rod, and it is pivoted about one end here, and it is moving in a uniform magnetic field, but it is moving with constant angular speed, omega. Okay, so it's rotating with constant angular speed, omega, in a uniform magnetic field. And our question is, we want to find what is the potential difference that is generated across its ends. Now, if we recall that we had a general result, that if we have a rod moving in a uniform magnetic field perpendicular to the magnetic field, the electromotive force was BL times V. That is B, the magnetic field, multiplied, not the electromotive force, sorry. The motional potential difference generated was BL times V. It is this, you know. Let me just remind you. Yeah, this. This is the expression that we have got. When we say that we have a conductor that is moving, a rod of length L moving with velocity V in a magnetic field, so the magnetic field is uniform to it, perpendicular to it, this is the potential difference that is generated across it. Here we had the whole rod moving with the same velocity V. Now let's see what we will get in our case, how we apply this to our case. Now, in our case, the issue is the following. Now, this rod is not moving with a constant speed, linear speed. It is moving with a constant angular speed. So that points at different distances from the pivot are moving with different linear speeds. You know, you recall that V is equal R omega. That is, this is a rigid body, and the speed of any point in a rigid body is equal, how far is this point from the center of the axis of rotation multiplied by omega. Okay, so different points here will have different V's. Not the whole rod does not move with the same V. So how we can proceed? Well, what we do is, as usual, we split this into small dRs, okay, infinitesimally small, and therefore, and for example, take one of these dRs. So the whole thing is split into small dRs. Consider one of these dRs. Now this dR is at a distance r from the pivot, and so this is now moving with a constant speed. So this is a rod, a small rod, infinitesimal rod, which has width dr, infinitesimally small, okay, and it is moving with speed or with velocity v, or with speed v. Now, in this case, the electromotive force or the potential difference across this will be bv multiplied by dr. We have a v now for this because, you know, this is infinitesimally small, so we can consider the whole thing moving with the same v in this case. And since it has infinitesimal length dr, then this is the potential difference or the electromotive force generated across these two, the elements of this. Now, if you want to find the electromotive force or the potential difference generated across the whole rod, then you have to add the potentials across each of these dRs together, and you find what is the potential difference between here to here. So this, the meaning of this by now, you know, is just to integrate over these two things. So integrating this gives you E, integrating this gives you this. Now, So that's what it is. Now, but V now here is a function of R, because what is V? V is omega R. Okay? V, you can take it outside. You have VdR, but V is omega R. Omega is constant by definition. This is more rotating with constant omega. So you can take it outside and you get the integral over R. How you integrate R? Over what? Well, evidently R varies from 0 to L, the whole length. So when you integrate this is a simple integral, R squared over 2, and so this is the electromotive force. And as you can see, it's a simple, elegant expression. It depends on how fast it is moving, the strength of the magnetic field, and how long is the rod, which all make sense.